Hi. In the last two videos, when we've been looking at the aromatic compounds, we've mainly been looking at benzene and benzene derivatives of aromatic compounds. But there are a number of aromatic compounds that are not benzene derivatives, so we're going to go over those today and then determine whether these are aromatic or non-aromatic. So a compound is aromatic if it meets two criteria. One, it has to be a ring composed of continuously overlapping p orbitals. And two, the number of electrons must fulfill 4n plus 2, which we looked at in the other videos. So to have continuously overlapping p orbitals, the ring must be planar. So I'm going to draw out two examples. Right, first one, benzene. It has p orbitals like this. Right, you have continuous overlap of these p orbitals. And benzene's planar. But if I were to have, this compound, for example, if I were to try to draw this out in 3D, it would look like, this is going to be difficult. You have these p orbitals, which would be overlapping, but then the ones here would be more pointing towards us and into the paper or into the whiteboard here. So you wouldn't have continuous overlap because these would be, the difference between these would be a 90-degree angle, because this part here is sticking up, so the p orbitals would be coming towards you and away from you rather than up and down. So this would not be aromatic because it's not continuous overlap of p orbitals. A second thing is you cannot have any sp3 hybridized atoms. Mainly carbon is what we're talking about. So, if you have this compound, it's not aromatic because right there you have an sp3 carbon, so there's no p orbital there, so you don't have continuous overlap of the p orbitals. Now, some aromatic compounds are ions. So I'm going to give an example here of an anion and a cation that fulfill the rules for aromaticity. So first, for the anion. Similar to what I just showed was not aromatic, but this time this is the compound. right? This is aromatic because I can draw resonance structures throughout the entire ring. So that means those electrons, that lone pair of electrons, it's delocalized and it spreads throughout the ring. And if I were to draw out the p orbitals in this ring, I would have p orbital, and then this lone pair here is inside a p orbital as well. So I have continuously overlapping p orbitals. It's planar. And the number of electrons, we have 6 electrons, which 4n plus 2 equals 6, 4n equals 4, so n equals 1. So that compound is aromatic because that lone pair of electrons is delocalized in part of the conjugated pi system. So next is going to be a cation. So I have a 7-membered ring here. This, I can draw a number of resonance structures here. That can move so now my cation's there. I can do it again. Oops, drew the arrow the wrong direction. I can do it again. So this time a positive charge is over here. Right, and I keep drawing resonance structures around the entire ring for it. Right, that means I have, again, a continuous network of p orbitals. The one where the cation is just an empty p orbital, but I still have a p orbital. The molecule is planar, and I have 6 electrons, which we know fits the 4n plus 2 expression. Right, so cations and anions can also be aromatic. Now the thing is, sometimes lone electron pair is not delocalized, so it does not count as part of conjugated pi system. So when determining if a compound is aromatic or not, one of the things you have to do is figure out if that lone pair of electrons counts towards the pi system. So an example is pyridine. That nitrogen has a lone pair. Now, is that lone pair part of the pi system? The way to figure that out is draw a resonance structure, right? If it's in resonance with the rest of the pi electrons, then yes, it's part of the conjugated system of the p orbitals. So if I try to draw a resonance structure here, I get and this does not work. I can't have 2 double bonds next to each other in a ring, because 2 double bonds next to each other has to be linear, but you can't be linear in a ring. So that means this pair of electrons here is not part of the pi system. However, a resonance structure I can draw with this compound, rather than the one I just tried, is to only move all the double bonds, which I can do. So all of those are part of a continuous set of overlapping p orbitals in a conjugated pi system. We have 6 electrons then, which we know corresponds to 4n plus 2, so this is aromatic. Another way we can know that this lone pair is not part of the system is if I protonate it. So I protonate it. I still have an aromatic compound, right? It's still aromatic. Because nothing changed with the 6 pi electrons from the 3 double bonds. Okay, another example here. I have this compound. There's 2 lone pairs this time that we have to figure out whether they're aromatic or not, or part of the system. So let's first start, I'm going to call this N1, and then down here is N2. So for N1, I'm going to try to draw this resonance structure. Drawing that now, I get plus and minus. If I draw another one, see I can move those electrons there and these up to here. So these electrons do seem to be delocalized because I can draw resonance structures with them throughout the ring. So N1 electrons are part of the conjugated pi system. Now what about N2? Okay, N2 now. Draw that resonance. Oops, I don't have the lone pair there anymore, because I moved it. The problem with this, again, we have 2 double bonds next to each other in a ring. So that is not a resonance structure, so N2 is not part of the system. So, determining how many electrons are aromatic here, we would have that lone pair plus the 2 lone pair, or plus the 2 pi electrons from each of the double bonds. So that means we have 6 total electrons, which we know matches 4n plus 2, so we have an aromatic compound. Right? Had the lone pair right here been part of the system as well, we would have had 8 electrons, in which case that would have been anti-aromatic. So it is important to determine which of the electrons are part of the system and which are not, to determine if your compound's aromatic, anti-aromatic, or non-aromatic.